Welcome to The Explainer, where we break down big topics in minutes. You've probably used tools like ChatGPT, but have you ever wondered what's actually going on inside? Today, we're going to peek under the hood and understand the core tech that makes it all possible.
Okay, so let's get right to it. GPT, it stands for Generative Pretrained Transformer. Now, the generative part, that just means it creates new text. Pre-trained means it's already learned from, a huge chunk of the internet. But honestly, the real star of the show, the invention that's driving this entire AI boom, is that last T word, transformer.
And that's the billion-dollar question, right? What exactly is a transformer? Well, to answer that, we're going to follow a single prompt on its journey, from the moment you type it in all the way through the system. We'll see step-by-step what actually happens inside one of these incredible models. Okay, Section 1, a simple prediction game. This is all about how these things actually generate text, because at its heart, a large language model is really just playing a surprisingly simple game. Seriously, it's not about being conscious or anything like that. Fundamentally, it's just trying to predict the very next word, or to be a little more precise, the next token, which is like a chunk of text.
So how does it do that? Well, it all happens in this simple repeating loop. First, it predicts the most likely next chunk of text. Then, it samples one possibility from that prediction. It sticks that new piece onto the end of what it's already written, and then it just does the whole thing all over again. Predict, sample, append, repeat, and it's that super simple cycle that lets it build up entire sentences, paragraphs, you name it.
So you might be thinking, does this simple loop really work? I mean, it sounds way too basic, right? And you'd be right to be skeptical. With the earlier models like GPT-2, it kind of didn't work that well. You'd get text that just didn't make a whole lot of sense. But here's where it gets crazy. When you scale everything up to the size of GPT-3, suddenly, almost like magic, this simple process starts spitting out text that's not just coherent, but genuinely creative. It's all about scale.
All right, on to part 2, words as coordinates, or how we turn language into math. Because think about it. Before a model can predict anything, it first has to understand our language. And computers don't speak English, they speak math. So the first problem to solve is how to turn our words into numbers it can actually work with.
And the very first step in that process is called tokenization. It's pretty straightforward. You just break the input text up into a bunch of little pieces called tokens. Now, a token can be a whole word, but it could also be just part of a word, like ing, or even just a piece of punctuation. Think of them as the model's basic building blocks of language. Okay, so once we have these tokens, each one gets turned into something called a vector. And a vector is really just a long list of numbers. But here's the cool part. You can think of that list of numbers as a set of coordinates. It's like we're plotting each word on a giant high-dimensional map of meaning. And on this map, words with similar meanings end up being neighbors. Now this is where things get really wild, because the directions on this map of meaning actually, well, they mean something. You can do math with words. The classic example you always see is this one. If you take the vector for king, and you subtract the vector for man, and then you add the vector for woman, the point you land on is almost exactly the same as the vector for queen. It's incredible.
And it's not just about royalty either. The model figures out all sorts of these abstract relationships on its own. Look at this. Italy minus Germany plus Hitler gets you close to Mussolini. Or how about this one? Germany minus Japan plus sushi equals bratwurst. It's learning these incredibly complex concepts about nationality, history, and even food, all just by looking at the relationships between words. It is absolutely wild. So when I said this map of meaning was high-dimensional, I wasn't kidding. For a model like GPT-3, every single one of those word vectors has 12,288 dimensions. I mean, we can barely imagine 3 or 4 dimensions. This thing operates in over 12,000. That immense space is what gives it the power to capture all the subtle shades of meaning in human language.
Okay, Section 3, flowing through the network. So we've turned our words into these super complex vectors. Now let's follow those vectors as they begin their journey through the actual core of the transformer network.
So what happens is that our whole sequence of vectors gets fed through a series of repeating blocks. Each block has 2 main parts. First, there's something called an attention block. Don't worry about that for now. It's super important, but we'll come back to it. And then there's an MLP block, which is basically the part of the network that does the heavy-duty thinking and processing. And your data goes through this attention MLP combo over and over and over again.
With each pass, the vectors are getting refined, soaking up more and more context from all the other words around.
Now, this is a really important distinction to make. You have to think about two different things. On one hand, you have the model's weights. These are the 175 billion parameters it learned during training. This is the model's brain, its long-term knowledge. It doesn't change when you talk to it. Then, on the other hand, you have the data from your prompt. These are the thoughts that are actively flowing through the network. They are totally dynamic and are constantly being changed and updated as they move from block to block.
And that brings us to our final section, from math back to language. Okay, so we've taken a vector, we've pumped it full of context by passing it through the network, but it's still just a list of numbers. So how in the world does the model turn that final, super enriched vector back into an actual word that we can read?
Well, it's basically a two-step process. First, there's a step called unembedding. This is where it takes that final vector and compares it against every single token in its entire vocabulary. We're talking tens of thousands of them to produce a raw score for each one. These scores are called logits. Then, it takes that giant list of scores and feeds it into a neat little function called softmax. And all softmax does is convert those messy scores into a nice, clean list of probabilities that all add up to 1. So now you know the exact probability for every possible next word.
And this is where you actually get some control over the model's output. You've probably seen a setting called temperature. Well, what that little knob does is control how the model chooses a word from that final list of probabilities. In short, it's your dial for controlling randomness.
So if you set the temperature really low, say to 0, the model gets very predictable. It will always pick the word with the highest probability. This is safe, but it can also be pretty boring and repetitive, kind of like a trite derivative of Goldilocks. But if you crank the temperature up high, you're telling the model to take more risks and consider some of the less likely words. This can lead to much more creative and original stories, but you also run the risk that it will just fly completely off the rails and degenerate into nonsense. It's a trade-off.
So when you step back and look at the whole thing, this entire journey, from a word to a token to a vector, through all those network blocks, and finally back to a new word, it's all about one primary goal. It's about letting each of those word vectors soak up meaning from its neighbors, to get an understanding of the text that's way richer and more specific than what any individual word could represent on its own. It's all about context.
But that leaves one giant question hanging, doesn't it? We keep saying the vectors soak up context, but how? How do they actually talk to each other? How does the model decide which other words in the sentence are the important ones to pay attention to? Well, the secret, the real magic behind the transformer, is a mechanism called attention. And that's the revolutionary idea we're going to dive into next time.